Have you ever been in a concert hall, noticed how, after a few moments of messy applause, the crowd starts clapping in perfect unison? It's a strange and wonderful thing. No one gives an order, there's no conductor waving a baton, yet a collective rhythm emerges from the chaos. This phenomenon is called synchronization. It's a pattern woven into the fabric of the universe. We see it in the flashing of fireflies on a summer evening, the coordinated beating of our own heart cells, the orbits of planets. It's a universal language of order. For centuries, scientists have been fascinated. The story often begins with Christian Huygens. He saw two pendulum clocks on the same wooden beam swing into perfect opposition over time. Tiny vibrations through the beam nudged the pendulums until they found a shared rhythm. They were communicating and agreeing on a tempo, the first recorded classical synchronization. If you like clear science explanations, please like and subscribe for more simple guides to strange ideas. To truly appreciate the weirdness and wonder of quantum synchronization, it helps to first get a firm grasp on its classical cousin. The world we experience every day is brimming with examples. Think of a group of people trying to rock a car stuck in the mud. At first, their pushes are uncoordinated and ineffective, but soon enough, they instinctively find a rhythm, heaving in unison, and the car begins to move. Their individual efforts have synchronized to produce a more powerful, collective force. This is a simple, intuitive example of how coupling, in this case, the shared goal and physical feedback from the car, can lead to a unified rhythm. Nature is the ultimate master of synchronization. Consider the mesmerizing sight of thousands of fireflies blinking in unison across a dark meadow. Each firefly has its own internal biological clock, telling it when to flash. If they were all isolated, the field would be a sea of random twinkling lights. But they are not isolated. They see the flashes of their neighbors. This visual coupling acts as a signal, nudging their internal clocks to speed up or slow down slightly. Over time, this network of tiny adjustments leads to the breathtaking spectacle of a whole population flashing as one. It's an emergent property, a large-scale order that arises from simple local interactions. This principle is so universal that mathematicians have developed elegant models to describe it. One of the most famous is the Kuramoto model, proposed in the 1970s. It imagines a population of oscillators, spinning tops, neurons firing, each with its own natural frequency. The model shows that if the coupling or the strength of the interaction between them is strong enough to overcome the differences in their individual frequencies. Now, let's take that classical idea and shrink it down, way down. Imagine our oscillators are no longer pendulums or fireflies, but the fundamental constituents of reality, single atoms, tiny quantum magnets known as spins, individual particles of light called photons. These systems are ruled not by the familiar laws of Newton, but by the counterintuitive rules of quantum mechanics. Quantum synchronization is the process by which two or more of these tiny quantum systems, each with its own natural oscillation, begin to move in lockstep. They develop a shared phase, or a common rhythm, just like their classical counterparts, but the way they achieve it is profoundly different. At its heart, the concept remains simple: tiny things ticking together. For instance, an atom can be excited by a laser, and the electron inside it will oscillate between different energy levels at a specific frequency. This is, in effect, a tiny atomic clock. Now imagine you have two such atoms. If they are left alone, they will oscillate independently, each at its own slightly different frequency, completely oblivious to the other. But if you create a way for them to talk to each other, perhaps by placing them close together, or, as we'll explore, by connecting them via a shared field of light, they can begin to influence one another's rhythm, eventually settling into a synchronized state where they oscillate as one. Why is this so much stranger than classical synchronization? Because quantum objects are fundamentally fuzzy and uncertain. A classical pendulum has a definite position and a definite speed at any given moment. A quantum oscillator does not. According to the principle of superposition, it can exist in a combination of multiple states simultaneously. An atom isn't just in state A or state B, it can be in a delicate quantum blend of both at the same time. This inherent uncertainty and fuzziness mean that a quantum rhythm is not as clear-cut as a swinging pendulum. It's a dance of probabilities, a ghostly oscillation that only reveals its definite nature when we measure it. So, when we say two quantum systems are synchronized, we are saying something much more subtle than they are ticking at the same time. We are saying that their probabilistic wave functions, the mathematical descriptions of their quantum states, have become correlated. the uncertainty of one system becomes linked to the uncertainty of the other. Measuring the state of one atom instantly tells you something about the state of its synchronized partner, even if they are physically separated. This connection, born from their shared rhythm, opens up a world of possibilities that simply do not exist in the classical realm, hinting at new ways to build better technologies. They act like Huygens' wooden beam, providing channels for tiny oscillators to find a common pulse, creating order that's strange and potentially revolutionary. The story of quantum synchronization becomes truly unique when we add the secret ingredients of quantum mechanics. These are the features that have no parallel in the classical world, and they transform the simple act of ticking together into something far more bizarre and powerful. The first of these is superposition. For any kind of synchronization to occur quantum classical, there must be a pathway for communication. The oscillators need a way to influence each other. Huygens' clocks had the wooden beam. Fireflies have the light they can see. In the quantum world, this communication happens through an unseen handshake. It's a form of interaction, or a shared environment acting as the coupling medium. Scientists have developed ingenious methods to create these quantum communication channels in the lab. They build the stage, where tiny dancers coordinate. One powerful technique uses a cavity. Two highly reflective mirrors facing each other form the cavity. Light can bounce between them many times before escaping. Place two quantum oscillators inside that cavity. For example, two atoms. They both interact with the trapped light. One atom can release a photon into the cavity. That photon travels and interacts with the second atom. It carries the rhythm of the first atom, nudging the second. The cavity is a shared bus, a common space to exchange rhythmic information. Slowly, their phases align. Another coupling mechanism is a shared environment, especially a shared source of noise. Normally, noise seems like the enemy of order. It's random static that disrupts signals. But the right shared noise can paradoxically cause synchronization. Imagine two boats bobbing in a lake. Both boats get pushed by the same waves. Their motions become correlated. The story of quantum synchronization becomes truly unique when we add the secret ingredients of quantum mechanics. As we've touched upon, a classical clock has one single, well-defined phase at any moment. A quantum clock, however, can exist in a superposition of many different phases at once. It's as if a pendulum were simultaneously at the beginning, middle, end of its swing, all at the same time. This fundamental fuzziness changes the very nature of what it means to be in sync. This leads directly to the Heisenberg uncertainty principle, which places fundamental limits on what we can know about a quantum system. For an oscillator, it means there is a trade-off between how well you can know its phase and how well you can know its amplitude or energy. You can have a state with a very precise phase, but its energy will be highly uncertain and vice versa. This property can be exploited in synchronization. For example, synchronized quantum systems can enter squeezed states, where the uncertainty in their collective phase is reduced below the normal quantum limit, at the expense of increased uncertainty in their energy. This phase squeezing is a purely quantum effect, and is a telltale signature that something more than classical synchronization is happening. Perhaps the most famous quantum twist is entanglement. Entanglement is a special kind of correlation that Einstein famously called spooky action at a distance. When two quantum systems become entangled, they are no longer independent entities but are part of a single unified quantum state. Measuring a property of one particle instantly influences the corresponding property of the other, no matter how far apart they are. While synchronization can occur without entanglement, the presence of entanglement represents the deepest level of quantum connection. Synchronized systems that become entangled are not just marching to the same beat, their very existences are intertwined. If you discover one is carrying a red flag, you instantly know the other is carrying a blue one, because their properties were linked from the moment they fell in step. This deeper layer of correlation is what makes quantum synchronization a potential resource for new technologies. They are distinct but related phenomena. So, if quantum synchronization is happening in a lab, hidden away in a tiny cold apparatus, how do scientists actually know it's there? They can't just look at it like they could with Huygens clocks. Instead, they have to rely on a series of clever measurements that act as signatures, or fingerprints, of this collective behavior. These measurements are designed to look for the different layers of correlation that build up as the systems fall into step. Simple, classical-like phase locking deep quantum connection in Tenkankama. The toolbox for detecting synchronization is a crucial part of the research. The first and most straightforward sign is phase locking. Scientists will repeatedly prepare the quantum systems in their initial, unsynchronized states and let them evolve. They then perform measurements to determine the average phase of each oscillator. If the systems are synchronizing, the difference between their average phases will shrink over time, eventually settling down to a constant value. They also look at the frequencies. If the oscillators lock their rhythms, their measured frequencies will converge to a single, common value even if they started out with different natural frequencies. Beyond just the average behavior, researchers look for correlations. A correlation means that the measurement outcomes of the two systems are no longer independent. Knowing something about one tells you something about the other. One powerful way to quantify this is by measuring something called mutual information. As synchronization builds, the mutual information between the quantum oscillators increases, signifying that a communication channel has been established between them and their fates are becoming linked. The ultimate sign of a deep quantum connection is, of course, entanglement. Proving entanglement is more demanding. It requires a specific set of correlation measurements that can violate a mathematical inequality, known as a Bell inequality. If the measured correlations are stronger than any classical theory could possibly allow, it serves as definitive proof that the systems are entangled. Detecting entanglement in a synchronized system is a major achievement. It confirms that the shared rhythm is not just a classical echo, but is mediated by genuinely quantum effects, opening the door to using that synchronized entangled state as a resource for quantum technologies. Now that we have a sense of what quantum synchronization is and how it works, the big question is, what can we do with it? One of the most direct and compelling applications is in the field of timekeeping. The development of atomic clocks, which use the incredibly stable oscillations of atoms as their pendulum, has already revolutionized technology, enabling everything from GPS navigation to high-speed financial trading. Quantum synchronization offers a way to push the frontiers of precision, timekeeping even further by networking these clocks in a fundamentally new, quantum mechanical way. Imagine not just one ultra-precise atomic clock but a network of them. If these clocks can be quantum mechanically synchronized, their collective timekeeping can become more stable and precise than any single clock on its own. The synchronization averages out the individual quantum noise of each clock, leading to a more reliable overall rhythm. This is particularly important for applications that require a common time standard across different locations. For example, a global network of quantum synchronized clocks could lead to a next-generation GPS system with unprecedented accuracy, capable of pinpointing locations down to the millimeter scale. This technology could also be vital for fundamental science. Many experiments in physics, such as radio astronomy arrays like the Event Horizon Telescope, rely on synchronizing clocks over vast distances to combine data from different observatories. Better clock synchronization would allow for even sharper images and more sensitive measurements. Similarly, experiments searching for gravitational waves or subtle variations in fundamental constants could benefit enormously from the enhanced stability offered by a network of quantum synchronized clocks, allowing them to detect fainter and more distant cosmic events. Furthermore, the robustness of quantum synchronization might offer new ways to build clocks that are more resilient to environmental disturbances. As we've seen, certain types of shared noise can actually induce synchronization. It might be possible to design clock networks that cleverly use their shared environment to maintain their lockstep rhythm, making them less susceptible to thermal fluctuations or electromagnetic interference that would throw a single clock off. While building and maintaining such a network is a formidable engineering challenge, the potential payoff, a global time standard of unparalleled accuracy, makes it a tantalizing goal for physicists and engineers alike. While better clocks are a fantastic prospect, the applications of quantum synchronization extend far beyond just keeping time. The same principles that allow oscillators to lock their rhythm can be harnessed to build incredibly sensitive sensors. The core idea: a group of synchronized quantum systems acting as a single, collective antenna. If a very weak external signal perturbs the system, like a faint magnetic field or a tiny gravitational distortion, it affects all the oscillators similarly, subtly shifting their collective phase. Because they act in unison, this tiny shift is amplified, so it's much easier to detect than a single noisy oscillator. This could lead to a new generation of quantum sensors with extraordinary sensitivity. For instance, synchronized arrays of quantum spins as magnetometers, detecting minuscule magnetic fields produced by the human brain, offering a non-invasive window into neural activity. In geology, such sensors could detect subtle changes in rock density, groundwater levels. Perhaps most excitingly, networks of synchronized quantum oscillators for gravitational wave searches, the faint ripples in space-time, created by cosmic cataclysms like colliding black holes. A synchronized network could detect frequencies current detectors miss. Another major area poised to benefit is quantum communication and quantum computing. A quantum computer relies on maintaining delicate quantum states of many qubits. A quantum network aims to transmit those states between different nodes. In both cases, a shared sense of time and phase is absolutely critical. Quantum synchronization could provide the underlying clock signal for a quantum computer, ensuring all logical operations on the qubits happen in the correct sequence. In a quantum internet, synchronized nodes could more reliably receive and transmit fragile quantum information, helping to establish and distribute entanglement over long distances. Looking further ahead, some theorists speculate synchronization could be a resource itself. It might be possible to create novel phases of matter where the defining trait isn't spatial arrangement, but collective rhythmic behavior in time. Time crystals, other synchronized many-body states could have exotic properties we're only beginning to imagine. While these ideas are still highly speculative, they show quantum synchronization is not just a tool for improving existing technologies, but a new frontier revealing entirely new physical phenomena and computational paradigms. The ideas of quantum synchronization are not just theoretical musings, they are being actively tested and realized in laboratories around the world. These experiments are marvels of precision engineering requiring scientists to isolate, control, measure a handful of atoms, other quantum systems, in highly controlled environments. It's like trying to build and conduct a microscopic orchestra where the instruments are individual particles and their music is a quantum oscillation. These experiments are crucial for confirming theoretical predictions and taking the first steps toward functional synchronized quantum devices. A common experimental setup involves trapped ions. Scientists use electromagnetic fields to hold one or more individual atoms stripped of an electron hovering in a vacuum chamber. Lasers are then used to cool these ions down to near absolute zero, minimizing their random thermal motion. These same lasers can be used to manipulate the internal quantum states of the ions, making them behave like tiny, high-quality oscillators. By controlling the interactions between the ions, often through their shared motion in the trap, researchers have been able to demonstrate synchronization between a few trapped ion oscillators, observing them lock their phases and even become entangled. Another leading platform is optomechanics. In these experiments, the oscillator is a tiny, fabricated, mechanical object, like a microscopic diving board, a vibrating membrane so small that its motion must be described by quantum mechanics. This mechanical oscillator is coupled to an optical cavity. Light from a laser interacts with the tiny moving object, and this interaction can be used to cool it to its quantum ground state and to couple it with another oscillator. Scientists have successfully synchronized two of these tiny mechanical drums, watching as they begin to vibrate in unison, their shared rhythm mediated by the light field connecting them. These experiments are incredibly challenging. Decoherence is a constant enemy. Stray heat, stray vibration, can destroy the delicate quantum states. Therefore, the systems must be kept in extreme vacuum and cooled to cryogenic temperatures. Furthermore, controlling the precise strength of the coupling and measuring the resulting quantum correlations requires extraordinarily sensitive detectors and stable laser systems. Despite these hurdles, progress has been rapid. What started with two synchronized oscillators has grown to small networks. Researchers are developing techniques to scale up, pushing towards the goal of creating large, robust, useful, synchronized quantum networks. We began our journey the simple, familiar image of a crowd clapping in unison, a beautiful example of spontaneous order emerging from chaos. We've seen how synchronization extends to the subatomic world where quantum mechanics adds strangeness and power. Quantum synchronization is the story of how the universe's smallest, fuzziest, most delicate components can find a common beat. Their probabilistic dances merge into a collective chorus. Connection and interaction are fundamental forces creating order at every scale. The core idea is simple and compelling. Link quantum oscillators via a shared interaction or a shared environment, and rhythms lock together. This shared pulse is more than curiosity. It creates correlations that let systems act as one. The collective state can be more precise, more stable, more sensitive. At its deepest, this connection becomes entanglement, the spooky link, and a key resource for quantum tech. From classical pendulums to entangled atoms, same shared rhythm. The potential applications are transformative. Networks of quantum synchronized clocks could redefine time standards, enable next-gen navigation, and probe the cosmos more deeply. Quantum sensors could use synchronized responses to detect faint signals from the universe and from within our bodies. A future quantum internet could transmit information securely and efficiently between nodes, all marching to the same quantum drumbeat. Lab work today is laying the groundwork. This field sits at the intersection of fundamental physics, engineering, and philosophy. It forces questions about the nature of time, information, measurement, and how order arises from chance. Challenges remain scaling lab systems to real-world tech, but the path forward is clear. Like a few fireflies sparking a field of light, synchronized quantum systems today may prelude tomorrow's technological orchestra. The beat is just beginning.